Okay, Mr. Watson here, and in this video we're going to talk about heart rate regulation. So as we know, the heart is myogenic and continues to beat without tiring, and it will always continue to do that, okay? Unless a situation arises where the heart rate needs to increase or decrease, then the brain is going to get involved. Okay, so when the heart rate needs to increase or decrease, the brain gets involved. And this is known as heart rate regulation. Now, a specific part of the brain, in the medulla oblongata, there is a control center, specifically a cardiac control center. So you can kind of tell from the name there. And this cardiac control center, it receives information from sensory nerves and then sends direction to the heart through motor nerves, which we'll go on to in a little bit more detail shortly. So basically, from this cardiac control center in the medulla oblongata of the brain, we have cardiac control or heart rate regulation. Okay? So, the autonomic nervous system. Now, it's quite handy to remember this as automatic because it just happens involuntary. It involuntarily regulates heart rate, and as you can see from the last image, it determines the firing rate of the SA node. Okay? So, the higher the firing rate of the SA node, the higher the heart rate. Okay, as we've already gone through in the conduction system. So, we have these receptors in the body, which we'll also look into more detail in a moment. And these receptors are the ones that, via sensory nerves, send information to the brain. And that's the cardiac control center again in the medulla oblongata. And after these receptors have sent information via sensory nerves, the brain will then direct the heart through motor nerves. And our first motor nerve is the parasympathetic nervous system. Okay? This parasympathetic nervous system is part of the ANS, and it's responsible for decreasing heart rate, specifically during recovery. And we also have the vagus nerve there. This nerve, this motor nerve, has a specific name, and its specific name is the vagus nerve. Okay, so part of the parasympathetic nervous system and responsible for decreasing heart rate. So how that would look like, it would slow the firing of the SA node. Okay, so this little diagram animations just trying to emphasize that we would slow the firing rate. It obviously wouldn't be that slow, as you know, but just to emphasize. So on the other side of that, we have the sympathetic nervous system. And again, the sympathetic nervous system is part of the ANS, and it's responsible for increasing heart rate, specifically during exercise. And again, the sympathetic nervous system has this motor nerve, and the specific name is the accelerator nerve. So it's quite a good one to remember, because that accelerator nerve, accelerate should give you the link to increasing the firing rate of the SA node, which means an increase in heart rate. Okay, and that would send them much faster. So as you can see in that animation, it happened a lot faster. Okay, so let's now take a look at these information sources, the information sources that send information via sensory nerves to the brain. Let's take a look at them. We have three main sources of information, and the first main source is neural control, and this actually has three parts to it. Okay, but the neural control is a control mechanism. So the first one we have is chemoreceptors. Now these chemoreceptors are located in the muscles, the aorta, and other arteries. But let's have a look at what this means. Chemo, chemical composition of blood. And such as has it got CO2 in the blood? Do we have an increase of CO2 and lactic acid? So they're detecting changes, chemical changes in the bloodstream, such as CO2 and lactic acid. So, I mean, and this can be either way. They might sense an increase in oxygen, but if we're exercising, they're going to sense changes in blood composition. And if we're exercising, this change would be an increase of CO2 and lactic acid. So these chemoreceptors would then, via sensory nerves, give the information to the cardiac control center. And if we've had an increase in CO2, the CCC would say, okay, increase heart rate. Okay? The next receptors are the proprioceptors. These are located in the muscles, tendons, and joints. Okay, muscles, tendons, and joints. And proprio meaning force or motion. Okay, and what these receptors do is they sense motor activity. And the easy way to remember this, they sense movement. And that's why they're located in the muscles, tendons, and joints. So basically, when we start moving, i.e. we're exercising, these receptors send information to the brain. They say we're moving, we have more movement, an increase in movement. And the cardiac control center will like, okay, increase heart rate. Okay? If we were slowing down in the recovery stage, they would tell the cardiac control center, okay, decrease heart rate. So they sense changes in movement. The chemoreceptors sense changes in blood composition, higher or lower. Okay? And finally, to complete the neural control mechanism, we have the baroreceptors. Baro meaning pressure or stretch. So these receptors detect an increased stretch or pressure on the blood vessel walls, as you can see from that diagram, okay? So we've got arteries are in normal constriction and dilated. So these baroreceptors will detect changes in the stretch of the wall, okay? Or increased blood pressure. So if we have an increased stretch on the wall or an increase in blood pressure, we'll send that to information to the cardiac control center. So that is neural control. Moving on to intrinsic control. Okay, we have two parts of this. And the first thing we have when we exercise is we have temperature changes. We usually get hotter. And these temperature changes will affect two things. The first thing is the blood viscosity, which is the thickness of the blood. And as you can see on the left side of that image, high viscosity, we've got much thicker blood. Okay, on the left we've got thinner. If we have thicker blood, it's harder to flow. Okay, it doesn't flow as easy. Okay, so temperature changes will affect that. And it will also affect the nerve impulse transmission speed. Okay, so basically nerve impulse happening faster. Okay. We also have venous return changes. So as we know, we should know this from Starling's law, when we exercise, venous return increases, okay, which means we have an increased ventricle stretch. If you look at the left ventricle there, the right image will show a much larger stretch as it's increasing its EDV, its end diastolic filling. And this will increase the force of contraction because we need to eject the blood out of that ventricle. So, therefore, you increase stroke volume. So that's intrinsic control. So that's temperature changes and venous return changes. And finally, the last main source of information is the hormonal control mechanism. And adrenaline and noradrenaline, these hormones, are released from the adrenal glands. Okay? And what that does is it increases the force of ventricular contraction. Therefore, it increases stroke volume. It also increases the spread of electrical activity through the heart. So if we've got more impulses generating and a larger spread, then we've got an increase in heart rate, which means we've got an increase in cardiac output. So they are the three main information sources, three different control mechanisms: neural, intrinsic, and hormonal. Now, neural control mechanism is quite a popular question in exams. They like to ask about them receptors. Okay, so cardiac control. Based on that information from them receptors or from the intrinsic control or hormonal control, the cardiac control center will action an increase or decrease in the stimulation of the SA node. So therefore, heart rate will increase or decrease. Okay, it will raise or lower. So just going back to what we started at the start, the CCC. Okay, if we go down the parasympathetic nervous system, we are decreasing heart rate via the vagus motor nerve. Okay, decreases heart rate. If the CCC actions an increase in stimulation of the SA node, they will use the sympathetic nervous system, specifically the accelerator nerve. Okay, and it will increase heart rate. So they're our two motor nerves, but with specific names. Okay, so just recapping that from the start. Now, let's just summarize all of that. So this summary, first summary, we're going to do two summaries. This summary is the response to exercise. So we're now exercising, okay? We've got an increase in CO2 and lactic acid in the bloodstream. The chemoreceptors are picking up on that. We've got an increased stretch on the vessel walls, okay? The baroreceptors are picking up on that. Proprioceptors are picking up on the increased movement, the increased motor activity. So we're exercising, all these things are happening. We've increased in temperature and our venous return has increased. We've got a higher demand for oxygen. We need more blood going back. And we've released adrenaline and noradrenaline. Okay, so that hormone's released specifically, as if we remember, even before we exercise, in the anticipatory rise from the graph. So all of these things have happened, and the sensory nerves send information to the cardiac control center, located in the medulla oblongata, via motor nerves, specifically the accelerator nerve, because we're exercising, will increase heart rate. So sympathetic nervous system, increased stimulation of the SA node via the accelerator node, which I told us, to increase heart rate. That means we have a greater force of ventricular contraction, which means we have an increase in stroke volume. That means we have an increased cardiac output. So all of these things we should have known from the last video. And then obviously we're exercising. So these things we should know from the previous videos. We're just understanding what controls it. Okay, what controls it. Okay, and that is the CCC. But just to finish up, response to recovery. Well, we've actually detected an increase in oxygen. CO2 is lowering. We've had a decreased stretch on the vessel walls. Baroreceptors are detecting that. Decreased movement. We're not moving as much now. Decreased temperature. Venous return is lowering. And we're inhibiting the release of adrenaline and noradrenaline. Okay? So these, via sensory nerves, send information to the cardiac control center via motor nerves, this time the vagus nerve, to decrease heart rate. Okay? So lower the firing rate of the SA node. So parasympathetic nervous system, decreased stimulation of the SA node, vagus nerve, which I've just told you about, to decrease heart rate, therefore reduced ventricular contraction, reduces SV, stroke volume, slowly. I'll come on to that point in a moment, and decreased cardiac output. Now, the reason we have slowly in brackets is we need to continue moving, as we know from our graphs, our stroke volume response exercise, so we can clear out the waste products. Because the CO2 won't have completely disappeared, the higher amount. So we need to make sure we continue to deal with that. Okay, so that's why it would decrease or reduce slowly. Okay, and that's the summary. And that is how we have heart rate regulation. Okay, so the ANS regulating heart rate and determining that firing rate of the SA node. Okay, thank you.